In this video, we will explore sketching the graph of rational function. And these are the steps in sketching the graph of the rational function. First, find the domain of the function. Second, find asymptotes if any. Third, find the x-intercepts and y-intercepts. Fourth, which is optional, determine if there is intersection between the graph of f and horizontal asymptotes. Fifth, the sign analysis by using zeros of the numerator and denominator to determine where the function is greater than 0 or above the x-axis, or where the function is less than 0 or below the x-axis. Sixth, sketch the graph of the function f and its asymptotes, if any. So for this example, given the rational function f of x equal to 2x minus 2 divided by x minus 3. So before we start, let us try to factor this function. In the numerator, we can see that there is a common, which is 2. So let us factor out 2. And then the other factor is x minus 1. And the denominator is x minus 3. Since we can see that in this rational function there is no common, it means that there is no whole in this rational function. So first, let's find the domain. So the domain is, so we know that this is a fraction, and in a fraction or rational function, x minus 3 or the denominator cannot be 0. And the value of x that makes the 0 is 3. So it means that the domain of the function is all real numbers except 3. And then to find for the vertical asymptotes, since there is no common in this rational function, so the vertical asymptotes appeared when the denominator is 0, or vertical asymptotes are the zeros of the denominator. So we can write that vertical asymptotes appeared when the denominator is 0. So that is x equal to 3. So this is a line passing at x equal to 3. So we can write that, or we can graph that as this. So we graph this as x equal to 3, a vertical line passing at 3, and we label it as x equal to 3. And then for number 3, let us find the horizontal asymptote. And in finding for horizontal asymptote, this is based on the degree of the numerator and degree of the denominator. Since we can see that degree of numerator is 1 and degree of the denominator is also 1, so if the degree of the numerator is equal with the degree of the denominator, so we can say that horizontal asymptote is y equal to the leading coefficients, which is 2 over 1. So we can write that horizontal asymptote is y equal to 2. So let us graph the horizontal asymptote y equal to 2. That is horizontal line passing at y equal to 2. So this is the horizontal asymptote. And label it as y equal to 2. Then in finding for the x-intercepts and y-intercept, so x-intercept, we set y equal to 0. So we put the 2x minus 2 divided by x minus 3 equal to 0. So in finding for the x-intercept, this fraction is equal to 0 when the numerator is 0. Or you can write 0 as 0 over 1 and you can do cross multiplication. So we have equation 2x minus 2 times 1 is 2x minus 2, and x minus 3 times 0 is 0. So it is enough equating the numerator to 0. So 2x minus 2 equal to 0, we bring negative 2 on the other side. So we have 2x is equal to 2, and then dividing both sides by 2. So x is equal to 1. So this is our x-intercept. And to plot the x-intercept in our graph, x equal to 1. So we graph a point passing at this. And then for the y-intercept, we set x equal to 0. So we have y is equal to 2x minus 2 divided by x minus 3 and putting x as 0. So y is equal to 2 times 0 minus 2 over 0 minus 3, which is equal to positive 2 over 3. So this is the y-intercept. So let us plot the y-intercept as 2 over 3, which is this point. And then for the sign analysis, we're going to use the zeros of the numerator and the denominator to determine where the graph is positive or negative. So the zeros, so let us use the zeros of the numerator and denominator, and these zeros of numerator, as we found here in the rational function, the zero of the numerator is 1 and the zero of the denominator is 3. And these zeros are the x-intercept and the vertical asymptote. So 1 and 3. 1 and 3. And then putting this 1 and 3 on the real number line, so we put 1 on the left of 3. So this is 1 and this is 3. Then identifying the sign on each interval. So let us start using or a number here on the right interval. So the number here is, let's choose 4. So we will solve for f of 4. So f of 4 is 2 times 4 minus 2, then divided by x minus 3, which is 4 minus 3. And it will give us 6 over 1 because it's 8 minus 2 divided by 1. So 8 minus 2 is 6 over 1 is 6. So it means that f of 4, the sign of f of 4 is greater than 0 because it's a positive. So here we need to put it as a positive. And then for the other intervals, we can make use of the idea that since this 2x minus 1 is with multiplicity 1 or add power, and this x minus 3 is also add power, so we can say that the next sign is a negative because it should change the sign, and then the other one is positive. So we can write that because the question is where the graph of the function greater than 0 and where is it less than 0. So we can write that f of x is greater than 0 on the intervals. So we choose the positive. So they are in negative infinity to minus 1, both of them open, then union from 3 to infinity. So these intervals are open intervals because 0 is not included. And then f of x is less than 0 for the interval from 1 to 3. So now we are ready to sketch the graph of the function and its asymptote. So using the sign analysis on this interval, which is 3 to infinity, the sign is positive. It means that the graph is above. And 3 to infinity is on this part, and this is the area where the graph is above the x-axis. So either we're choosing to graph on this part on the other part. So we can choose a number on this area, which is x equal to 4, and we will try to know what's the value so we can be able to know if the graph is on this part or the other part. So let us try to know the value of f of 4, and I guess we already solved here that f of 4 is equal to positive 6. So when f of 4 is equal to positive 6, 4, 6 is above. So it means to say that the graph is on this part, not on that one. Okay, so let us sketch the graph, and we need to sketch the curve pausing at this point and asymptotic here and asymptotic there. So the graph will look like this. Okay, so just make sure that the graph is asymptotic on this line and the other line. So that's the graph on that part. And then next interval is from 1 to 3, which is negative, meaning the graph is below. So 1 to 3, let's locate 1 to 3, and the graph must be below. So it means that the graph must be here. on this part. That's 1 to 3, and the graph is below the x-axis. So we can see that there's a point here, an asymptotic there. So we will get the idea that the graph will looks like that. And make sure that your curve will get closer and closer in this asymptotic line. And once it's very close here, then you have to stop and put an arrow. So next is from minus infinity to positive 1. So in this interval, the sign is positive, so the graph is above. So it means to say negative infinity to 1, right? So negative infinity to 1 is on this part, so it should be above. So either on that side or on that part. So we can see that from minus infinity to 1, when the graph is above, there's a point here. So it means to say that the graph will look like this. Okay? So it's not on this part. It should be in the lower, which is above, but above the x-axis. So we can sketch this, connecting this x-intercept to this y-intercept, and then asymptotic on this line. So that's it. That's the graph of the function. And take note, in graphing rational function, you have to take note of the following. First is make sure that the graph is smooth, means there's no straight line. Okay? And with arrows on the end points. And the asymptotes are graphed as the broken line, like this vertical asymptote and this horizontal asymptotes. That's it. For the second example, given the rational function f of x equals this, so let us try to factor the numerator. So to factor this, so the factors of x squared are x and x, and the factors of 6 are 3 and 2. And then since we want the product to be as a negative, we were checking the middle term, which is negative, so we put a negative on the larger number, which is a minus 3 and a positive 2. And make sure that you will check the product of this before you continue. So multiply that, multiply this, this, and that. So the product, make sure that it's equal to this. And then divided by, for the denominator, let's factor again x squared as x and x. And then minus 2, so we have 2 and 1, putting the negative on the larger number, which is in 2. So minus 2 and a positive 1. And then make sure again that the product of this is equal to that. And then, so since we can see here that there is no common factor in numerator and denominator, so it means to say that there is no hole on this rational function. So we can now find the domain of the function. So for the domain of the function, since this is a rational function, the denominator cannot be 0. And the x values that makes this denominator 0 are positive 2 for this and a negative 1 for that. So it means to say that we can write that the domain is all real numbers except positive 2 and a minus 1. And then to find for the vertical asymptote, since there's no common factor, so vertical asymptotes are the zeros, all the zeros in this denominator. And the zeros of those denominators are, we put x minus 2 and x plus 1 equal to 0. So x is equal to 2 and x equal to minus 1. So make sure that you will write the vertical asymptote as 2 equation of the line like this. And just to take note, never write vertical asymptote as x equal to 2 and a minus 1. So don't write in this way. And another one is never write vertical asymptote as v dot a as equal to 2 and a minus 1. So never write in this way. And then for number 3, finding the horizontal asymptotes is we are identifying this according to degree of the numerator and denominator. And as we can see, the degree of numerator is equal to the degree of the denominator. So we can write that degree of numerator is equal to degree of the denominator So therefore, we can say that horizontal asymptote is y equal to the numerical coefficients or the leading coefficients of this numerator and denominator, which is 1 over 1, which is 1. So horizontal asymptote is y equal to 1. And let's have a note again. So never write horizontal asymptote as 1, which is horizontal asymptote equal to 1. And to find for the x-intercepts and y-intercepts, so in x-intercept, we set y equal to 0. So putting the function as x minus 3 times x plus 2 divided by x minus 2 times x plus 1, equating this to 0. So this fraction is equal to 0 when the numerator is 0 because denominator cannot be 0. Or what you can do is you can put the 0 as 0 over 1, then you can do cross multiplication. Like multiplying this there, which will give us x minus 3 times x plus 2 equal to multiplying this on 0, it will give us 0. So it means that when this fraction is 0, it is enough equating the numerator to 0, like this equation. So we can find here that x is equal to 3 and a minus 2. So here, since we're finding for the x-intercepts and not vertical asymptotes, we can write the x values in this way. So now we can plot this 3 and a minus 2. So 3 and a minus 2. So positive 3 is on this point and a minus 2 is on this side. So these are the x-intercepts. Then for the y-intercept, we put x equal to 0. So let us put the value of x, which is 0, on this function. So we have y is equal to 0 minus 3 divided by 0 plus 2 over 0 minus 2 and then 0 plus 1. Or you can simply substitute 0 in this original function here. I think it's easier substituting in this given. And then so let us simplify this since we have started this. So this is a minus 3 times a positive 2 and a negative 2 times a positive 1. So it will give us positive 3. So y equal to 3 is the y-intercept. So let us plot y-intercept at 3. Okay. Now let us do the sign analysis by using the zeros of the numerator and denominator, and these zeros are the x-intercept, and the vertical asymptotes. So if we will list them, it's 3 and a minus 2, and the vertical asymptotes are 2 and a minus 1, positive 2 and a minus 1. So let us draw this. Let us draw this in real number line. The lowest number is a minus 2, then minus 1, then positive 2, and then 3. And then we can find the sign on this f of 4. So if we will put f of 4, so we will get, uh, let us recall the function. The function is y equal to x minus 3, times x plus 2, then divided by x minus 2, x plus 1, x minus 2, and x plus 1. If we put 4 in x, so it will be 4 minus 3, then 4 plus 2 divided by 4 minus 2, and 4 plus 1. So let's find the value in case we need f of 4 later. So this is 1 and 6 is 6, then divided by 2 and 5 is 10. So this is 2 over 5. It's a positive. So this side or this interval, the function is above the x-axis, or it's a positive. And then let us check if there is an even power and odd power. All of these are odd power. So it means to say the signs is changing or alternating sign. So if this part is positive, the next interval is a negative, then positive, negative, and a positive. You can check, you can choose a number here, put in the function, then check if it's negative. So do the same here, do the same on the other, and on the last interval. So now we can write here that the function is positive on the intervals negative infinity to minus 2, which is this, and then negative 1 to positive 2, which is that, and from 3 to infinity. And then the other one is f of x is less than 0 on the two intervals negative 2 to minus 1. And then another one is 2 to 3. So that's the sign analysis. Now we are ready to sketch the graph of the function and its asymptote. So let us graph the vertical asymptote x equal to 2 and x equal to negative 1. X equal to 2. So let's draw that as a broken line. And then x equal to 2 and x equal to negative 1. So another here. And then the horizontal asymptote is y equal to 1. So y equal to 1 is there. Okay, so let us try to apply the sign analysis. And let us write the given function again in case we need an extra point. So we will have x minus 3 multiplied with x plus 2 divided by x minus 2 multiplied with x plus 1. And we can see here that f of 4 is equal to 2 over 5. So let us start on the first interval on the right, which is from 3 to infinity, which is above. 3 to infinity above is this part. And you can see there's two options again, either one or second option. But to select here, it's obvious that since there's a point here and then asymptotic on this line, so the graph will look like that. And we can confirm that the graph is there, not here, because f of 4 is 2 over 5, it's less than 1. So it should be somewhere here. So it means to say we can graph in this way. Next, for the next interval is 2 to 3, which is below. 2 to 3, which is below. This is 2 to 3, and the below part is this. So we can connect at this point, and then approaching on this vertical asymptote. So it will be like this. So let us graph it, then stop here. And then the next interval is from minus 1 to 2. Minus 1 to 2 should be above. Minus 1 to 2 is on this part. It should be above. And we can see a point here. It means to say it's not here. So since there's a point here and asymptotic on this line, so we can assume that the graph will look like that and can be like this. Okay, so to make sure, if you want, you can check a value of y value when x is 1 and when x is 0.5. So if you can check f of 1 or f of 0.5. F of 1, I guess f of 1 is equal to 4, no, it's 1 minus 3, 1 minus 3, and then 1 plus 2 divided by 1 minus 2, and then 1 plus 1. So this will give us negative 2 times a positive 3, and this one is minus 1 times 2. So it's also equal to 3. F of 1 is 3. And then it's impossible that after this point it will be like that. So you can have an extra point, which is f of 0.5, which I believe it is approximately 2.8. Okay, so let's have an extra point. So I'm putting this an extra point and this one. So now you can see that our graph will be closer to the real graph. So we can connect it like this and like that. Okay, and then for the last interval, which is minus infinity to minus 2, it should be above, and minus infinity. Sorry, I missed another interval from minus 2 to minus 1. From minus 2 to minus 1, the graph must be below. So it should be here, must be below. So connecting on this point, and asymptotic here, so the graph will look like this. And then for the last interval, which is minus infinity to minus 2, the graph must be above. If it's above, so it should be on this part. So there are two options. First option is here, the second option is there. Since there's a point here and asymptotic there, so it will be on this part. So connecting this, so that's the graph of the rational function. And take note, we have to make sure that the graph is smooth and means no straight line and with arrows on all the endpoints, and the asymptotes are graphed as the broken line, which is here y is equal to 1, here it's x equal to 2, and here it's x equal to minus 1. So that's the graph of this rational function. That is the end of this video. If you find this video useful, please like and subscribe and turn on the notification bell so you never miss out on the future content.